The term temperament refers to the tuning of musical intervals away from just intonation, which may be done for various reasons. Throughout history, there have been many systems of temperament. These include, among others, equal temperament, where one interval, usually the octave, is divided into equally spaced pieces; well temperament, where the chromatic scale was made unevenly spaced so as to favor the purity of certain keys without completely sacrificing others, as in Bach's well-tempered clavier; and meantone temperament, which was similar to Pythagorean tuning in that it used stacked fifths to generate its intervals, but instead the fifths were flatted so that they stacked up to produce purer thirds. In this video, however, I will be introducing you to what is arguably today's most relevant and thoroughly defined system of tempering, the regular temperament paradigm. The fundamental concepts of regular temperament are the generators and the mappings. Generators are intervals used in combination with each other to create all other intervals in a regularly tempered tuning. The mapping is what ratios of just intonation we say those intervals are approximating. You may notice that this method is reminiscent of meantone temperament. In fact, meantone temperament fits perfectly under the regular temperament paradigm, where the generating intervals are the fifth and the octave, and they are mapped to 3/2 and 2/1 respectively. Then, combinations of the two are used to arrive at other intervals like the major third, which is mapped to 5/4, or the minor third, which is mapped to 6/5. A more mathematically robust definition of the mapping specifies how many of each generator are required to reach each prime number of just intonation taken into account, thereby defining how to arrive at any just intonation ratio in terms of those generators. A useful convention is to refer to the larger generator in a temperament with only 2 generators as the period. So then, in meantone, 2/1 is mapped to 1 period, the octave, 3/1 is mapped to 1 period plus 1 generator, a perfect 12th, and 5/1 is mapped to 4 generators, a major third up 2 octaves. An interesting repercussion of mappings like this one is that commas, small ratios close to 1/1, cease to exist in the system and are equated with 1/1, or the unison. This is called tempering out that comma. In most mathematical contexts, it would be gibberish to equate any non-1/1 ratio with 1/1. But in tuning theory, it is one of the most revolutionary concepts in recent history. In meantone temperament, the comma 81/80, also known as the syntonic comma, is tempered out. We can show this starting with how 5/1 is mapped to 4 generators. That means 3/2 to the 4th equals 5/1. Expanding 3/2 to the 4th, we get 81/16 equals 5/1. Finding a common denominator gives us 81/16 equals 80/16. Then we can multiply both sides by 16 and get 81 equals 80. Then finally, dividing both sides by 80 gives us 81/80 equals 1/1. The meaning behind this seemingly meaningless statement is that in a tuning that tempers out 81/80, all ratios that differ by that comma will be represented by the same interval. This has 2 important implications. One is that chord changes that would drift by 81/80 in just intonation now return to the same note you started on, eliminating chromatic drift for that comma. The second important implication is that we are given a way to represent one dimension of just intonation, the dimension of the prime 5, in terms of 2 other primes, 2 and 3. In doing so, we are approximating a 3-dimensional structure with only 2 dimensions, therefore lowering the complexity. It is only an approximation, however. As you may notice, if we treat a pure 81/16 as our 80/16, or 5/1, by definition it'll be out of tune with respect to 5/1. Here is the 1-6-2-5 progression using pure fifths and using 81/64 as our 80/64. But not to worry, As history already dictates, if we temper all 3 over 2s in the system, that is to say, regularly temper them, then stacking 4 generators arrives at a much purer 5 over 1. Here is that same chord progression in several different meantone tunings that form a compromise between the ratios of 3 and ratios of 5. In addition, we could slightly temper 2 over 1, the octave, to reach a compromise in purity between all 3 primes we're representing. Doing so can result in a remarkably good approximation of just intonation for such a simple, 2-dimensional structure. Here's the 1-6-2-5 chord progression, tuned to an optimized meantone tuning. As we'll find out in the next video, the use of generators to define a tuning's intervals has additional benefits not related to harmonic purity or chromatic drift.